Welcome. Let us talk about query execution. Here we need to discuss about the sort and the join operators. Take a look what happens in some of the project ideas, but I skip this project ideas because look at the overall query processing what we discussed so far. Starting with the SQL query, you parse, and then what you get is a parse tree. Now the parse tree is needed. Why? Because you want to develop a logical query plan, you need to do query rewriting. So after the parse tree, you rewrite the queries, you develop a logical query plan, and from logical query plan, you develop actually choose one of the best logical query plan, and then you develop many physical plan based on stats and heuristics. And then after the physical plan generation, you have a physical query plan, and then you execute and finally see the results. So what is the roadmap? A simple operator, nested loop join. These are actually some of the issues we need to talk about: cost model, clustering, operator classes, and operator implementation, how we do scan based, sort based, using existing indexes, and hash based. How do we manage buffer, and is there any way we can do parallel processing? That's something very, very important. Take a look at nested loop join. We have two relations. You can see R1 and R2. And in this relation, we have at least 6 tuples each, and I'm taking a natural join. So what happens? Nested loop join conceptually, for what you do for each tuple in relation R1, right? You do for each tuple S in relation R2. If, because you are actually doing natural join, so the equality, the same field must be same. So R dot C S dot C, then output R dot S pairs. All right. So we can have two types of operations. What we can do by tuple, we can do by block, or we can do asymmetric. Now, implementation operators, there are basic algorithm. What we call is a nested loop join is scan based, sort based, using existing index file or hash based, and we do memory management and parallel processing. So talking about the cost model. Cost model, first of all, is a very important concept. What we mean by cost model is cost in terms of time. How? You are counting number of disk blocks that you read and write during operation execution. That is the simplest way you can say a cost model. Now, extends to query plan. Cost of query plan is sum of all the operator costs. That means for each operation you have certain number of disk read write, and each disk read write needs a certain operational time. That's actually all together is the cost model. But what is the caution? You really have to ignore the CPU cost, because CPU has its own clock, and based on the clock speed there is a timing, but we can simply ignore that because that's a very small time unit. Now what are the assumptions we have? Single processor, because that's actually you have to consider, and we'll consider parallelism if it happens to be later. Ignore cost of writing out results, and ignore number of accesses to index blocks. Now parameters used in the cost model, there are 4 parameters. What you see, B of R, that means we are talking about number of blocks storing R tuples. B means block, so B of R means you are talking about number of blocks that you are storing R tuples. T of R, number of tuples in R. V of RA means number of distinct values of attribute A in R. So V of R means you understand we are talking about distinct values of attribute A in R, and M means the number of memory blocks available. So let's take a look at the clustering. Clustered, the file organization, you may have 2 different types of cluster: R1, R2, S1, S2, R3, R4, S3, S4. Sometimes clustered relation, that means the relations are in a different cluster, and you can have a cluster index. So clustering index, you can see tuple with a given value of the search key packed in as few blocks as possible. That means we are talking about the search keys are in blocks. So what is the advantage? I'm not going to search the whole index region, but I'm going to search a small block which takes less time. So the entire idea of clustering index is to minimize the read write time, because you have to save time. If you know which cluster, you have a very small space to search, you save time. So an example, you see T of R is 10,000. You can understand that we are talking about 10,000 tuples and we have a block of 200. So if R is clustered, then number of R tuples per block is that, and it actually happens to be that way. So operator classes, you see what happens here, that you have a tuple at a time and full relation. You have select and sort operation and binary differences. All right, so let's take a look at the scan based implementing tuple at a time operator, one pass algorithm. There are actually concept is that you scan first, then process tuples one by one, and then write the output. And how do you calculate the cost? Cost is the block of the relation R. Remember, cost is the number of input-output operations, and we ignore the cost of write output. So implementing the full relation operator, example sort. Suppose T of R is multiplied by tuple size of R less than equal to memory size multiplied by the block of R. So read R completely into memory, the relation, and then sort, and then write output, and the cost is P of R. So implementing a full relation operator sort, suppose R, if the R is not fitting within the memory blocks, M blocks, consider a two-pass algorithm for sort generates to a multi-pass algorithm. Read R into memory into M size chunk, and sort is chunk in memory, and write the output. Merge all sorted sublist and write the output. So what happens? You are actually processing by chunk in the memory, because you cannot fit the whole relation in the memory, but you take by chunk and ultimately sort them and finally merge them together. So this is called two-pass sort phase 1. Suppose this B of R, we are talking about the block 1000, and R is clustered, of course, and M you can understand is 100. So you are actually having a relation R, and then you have a memory by chunk, ultimately sorted sublist, and then all sorted sublists joined together. Phase 2, what happens? Because you all have a sorted sublist now as an input, you are coming into the memory, and then ultimately you produce a sorted relation. So we call this algorithm two-pass algorithm. So phase 1 and phase 2, we have two different ways to sort. So analysis of two-pass sort is that what are the costs? We basically have 3 times B of R if R is clustered, or B of R plus 2 B of R prime, otherwise the memory requirement is of the order of 1 by 2. So duplicate elimination comes into another discussion, because suppose you have a block of R is less than M and M is clustered, use in-memory index structure. So what is the cost? Cost is the block of R, of course. Can we do with less memory? If B of rate of change of R is less than the memory, aggregation is smaller to duplicate elimination. Duplicate elimination is an important issue in cost model. So duplicate elimination based on sorting, sort then eliminate duplicate, because sort and then the duplicates will come one after the other, so and you can remove them. So what is the cost? Cost is cost of sorting, because you need to sort first and then the block that you are reading in the R. But can we reduce the cost further? Yes, eliminate duplicate during the merge phase we can actually eliminate. So block of nested loop join is like this. We have two relation R and S, and ultimately conceptually we know what we are doing. This is actually our first discussion we did. Analysis of tuple based nested loop join, cost of R as outer, and then you basically have T of R plus T of R multiplied by T of S, and cost of S as outer if it happens, that outer and inner, and then ultimately block based nested loop join. Suppose R is outer, and then in that case the block of R, you basically have a relation of block with the memory size -1, because you are in a place where you already have the block and then block of S. So What if S is the outer, then actually you are replacing the B of R with the B of S and you have the same calculation done. So let us work out in a nested loop join example. Relations are not clustered. For example, we have a number of tuples 10,000, two relation. We have one tuple, one relation has 5,000 tuple, another relation has 10,000 tuple, and 10 tuples per block for R1, and for R2 M is 101 block. So tuple based nested loop join cost for each tuple R1, you basically have 10,000 read tuple 1 plus read tuple R2 5,000. So you are actually all together you are actually having 50,000, 50 times 10 to the power of 6 input outputs. So you can understand that it is a very high cost. So can we do better when R and S are not clustered? Use our memory. Read 100 blocks worth in R1 tuples and then read all R2 and join repeat until done. So we try to utilize more memory in order to reduce disk IO input output cost. So cost for R1 chunk, read chunk 10,000 IOs, 1,000 IOs, R2 5,000, total 6,000. So the total cost is come down, you see, now to 60,000 IOs. Compare 60,000 versus this. What a reduction. We reduce this cost, and practically because we actually use more memory in order to reduce disk IOs. So can we do better? If we do reverse join order, R2 natural join with R1, it happens to be much smaller. We at least come down to another 5,000. So now 55,000 input outputs. So you can understand that you have a better management if you plan well. So example continued, if you nested loop join R2 R1. Now suppose relations are clustered. See, for each R2 chunk you have 100 outputs. Read R1. So the total chunk you are reading actually 5 chunk times that. So you can understand if it is clustered, you are reducing by 1/10. You say 5,500 versus 55,000. So it's come down. So we prefer clustered operations. So join with sorting, sort merge join operation, it happens to be like this. So if R1 and R2 not sorted, then you sort them, that's one time. And then for each value of I and j, while you are actually sorting, you have actually comparison between R1 and R2C, and finally you sort it. So procedure output tuples, you actually generate output tuples based on the sorting. An example of R1 and R2C, you can see this example. So block based sort merge join, you have actually block based sort and block based merge operations, and it's actually again two-phase algorithm, two-phase sort. You first read the entire relation and then get into the memory, sort it, and sorted sublist come into the memory, and finally produce the sorted R. So sort merge join operation is a very known operation. You basically have two relations you are sorting and then finally merging them. So sort merge join operation cost actually it happens to be, if it happens that you have, it is at least 5 times the block size of relation R and S and the memory management like this. So it happens to be like R1 R2 clustered but unordered, and the total cost, sort cost plus join cost, is about 7,500 input outputs, but NLJ cost is 5,500. So merge join does not really pay off because merge join takes more input output cost. However, NLJ cost is actually quadratic because you see happens to be the join operation always takes actually higher cost. Okay. So can we improve the sort merge join? We can actually, do we need to create the sorted R1 and R2? That's the practical feeling, but that's actually no choice because when we are merging, they are already sorted. So a more efficient sort merge join is like this: sorted sublist and then finally apply the merge algorithms. So analysis of efficient sort merge join operation happens to be like this, and I skip this also. So memory requirement in it depends on the block size, and also we can skip this. These are actually join operations using existing indexes, and practically happens to be that ultimate plan is that find a cost model. So that's the whole thing, and we actually have some certain assumptions in terms of index, in terms of cluster, and we do the calculation of cost. R2 reads 500 input output, so for each you probe the index, and if match then read R1 tuple. So you are actually checking the index and then get the data, that's kind of thing happens. So what is expected number of matching tuples? You have, it depends on at least one tuple expected for each combinations. And what is expected number of matching tuples if you have this kind of data manipulation operations? So the total cost of index join in non-clustering index, it happens like this, but definitely it's higher than the normal. So what if index does not fit in the memory? If it happens that you have to get into the block. So say R1.c index is 201 blocks. So keep root plus 900 leaves nodes in the memory. Expected cost is at least, total is about 0.5 in terms of the values. So the total cost calculation comes like this, but the entire idea is that the block based nested loop join versus index based nested loop join. What you see, you have actually different join operations in terms of costing, and find the optimal cost plan. So sort merge join with indexes, you can avoid sorting, and you have zigzag join like this. So far it happens to be like this, that you may have nested loop join, and then you have a merge join, you have a sort merge join, and using different indexes. So building index on the fly for join, you may have hash join, it is a conceptual, and hash function you are applying, and then create a bucket, and ultimately each bucket is filled with a value. So what you do, the algorithm, hash R1 tuples into G1 up to GK, and hash R2 tuples, and then for each whoever is matching, put them into the buckets. So that's actually hash join operation continues, and you have different buckets. I skip this also. These are actually different cost model. You can take a look. The minimum memory requirement happens to be for the operations, and keep some buckets in the memory also, and almost the bucket size, it depends on the size of the blocks, and you have a join remaining blocks in such a way that you produce better representation. So the entire idea is again cost calculation based on buckets. You have a certain bucket size, certain number of operations, you do calculate the total cost in terms of operational time. So how many buckets in the memory? Again, that question is coming. And another hash join trick is like this. So I think we understand the entire discussion plan is to find the cost in terms of different operators and operations. So for hash based versus sort based join operation, there are some similarities, some dissimilarities. Non-equi joins, first of all, memory requirement, because memory requirement is so different, and sort order may be useful later. So the summary is that nested loop joins for small relations better, because for equi-join, however relations are not sorted and not index exists, hash join is usually best. So sort join merge, SMJ we sometimes say sort merge join, good for equi-join. If relation already sorted, use merge join, because you don't have to sort it. If index exists, it could be useful for operations, and join depends on this. So these are actually buffer management issues. DBMS buffer management is very important, because you're talking about reading high amount of data in out from the disk. So many control memory directly. It may control the memory directly, and these are actually buffer replacement policies. You have least recently used, sometimes LRU, we say least recently used. Some data you are not using very often. So these are actually LRU, second chance, most recently used, and FIFO. So interaction between operators and buffer management, your memory may change while an operator is running. Some operators may take advantage of specific buffer management. So join strategies for parallel processors, it may happen that we can actually talk about it later when it comes our time. So that's all about the roadmap and the discussions, and we stop here and hope you really enjoyed this very complex process.